Alright, so in this particular tutorial, what I'd like to teach you how to do is determine what kind of amino acid you're looking at if you're given a particular amino acid. Now, what I'd like you to notice is that in every instance, part of these amino acids is exactly the same. Notice every single amino acid has an amino group, a carboxyl group, and those are going to be around an asymmetrical carbon. Then we have a hydrogen, and then we have the distinct R group that determines the chemical nature of the molecule. So whenever you approach an amino acid and understand that some of these may not be in this form, as you'll see in your book, the amino and carboxyl groups are in their ionized forms. You have to keep that in mind. But when you approach an amino acid, the first thing I'd always like you to do is find your asymmetrical carbon, so it's going to be sandwiched between a carbon and a nitrogen, and it's going to have a hydrogen on one side. Find the hydrogen on each of the asymmetrical carbons and look exactly opposite it to see what the R group is. So here's the R group, here's the R group, here's the R group, and here's the R group. Now that we know what our R groups are, we can determine what kinds of amino acids these are. And this is going to be based on either the functional groups or the presence of a charge. Okay, so let's start up here. This, as you may or may not recall, hopefully you do, is a methyl functional group. It is the only non-polar functional group. And because this is the only thing extending off of this asymmetrical carbon in our R group, that means this is going to behave in a non-polar manner. So this is going to be a non-polar hydrophobic amino acid. Okay? Let's move over here. This one's a little trickier. And the thing that trips up a lot of students is that they see the methyl group and think that because it has a methyl group, it's going to behave in a non-polar fashion. While that may be true here, this is a hydroxyl group. And you'll recall that it behaves in a polar manner. So even though we have this non-polar functional group, this allows this functional group, this R group, to act in a polar manner. And as a result, we classify this as a polar amino acid. So if the functional group extending off the R group, if all of the functional groups at the end of that chain are nonpolar, then it's a nonpolar amino acid. But if you have some functional group at the end of your R group that is polar, it's going to allow that R group to behave in a polar manner. Okay? And you'll notice that a lot of the amino acids that we see that are classified as polar are either going to have a hydroxyl group, an amino group, a carbonyl group, or a sulfhydryl group. Those are all those polar functional groups that we learned about. Alright, finally, we know that each of these are those charged amino acids, which means that they either have to be acidic or basic. Now, for the acidic ones, it's pretty easy to recognize because this is actually an ionized form of the carboxyl group. And you'll remember that anything that contains a carboxyl group is classified as an acid. And this is as well. The other thing to remember is carboxyl groups normally look like this. C, double bound to an oxygen, bound to an oxygen and a hydrogen. Notice this one's missing its hydrogen, which means in this particular solution, it gave up that hydrogen. And from chapter 3, hopefully what you'll remember is anything that increases the hydrogen ion concentration of a solution is also classified as an acid. So we classify this as an acidic amino acid for two reasons. One, it has a carboxyl group, but the other reason, the more important reason, is that because when we have that carboxyl group here in that ionized form, it actually represents us giving up a proton, thereby increasing the proton concentration of the solution, making this substance an acid. Okay, so let's come to our final amino acid here. This one is classified as a basic amino acid. Now let's explore why. First and foremost, this looks like a variant of that amino functional group that we saw. Okay? And remember, amines typically act as bases. But if we also want to look at it, what it does here, notice this particular region of this R group has an additional hydrogen, giving it a positive charge. Because it bound to that hydrogen, technically what we're doing here is decreasing the proton ion concentration. Okay? So whereas here we increase the proton concentration with this carboxyl group, here we're decreasing it, and you'll recall from chapter 3 that anything that decreases the proton concentration is classified as a base. So the two reasons why we can classify this as a base: this is a derivative of the amino group, and anything that had an amino group was classified as an amine, but this group also has the tendency to act as a base. The way it does that is by accepting the protons, thereby decreasing proton concentration. And that is the definition of a base. So these are the 4 different types of amino acids: nonpolar, polar, acidic, and basic. So we know this now based on what functional groups or what arrangements of atoms we see in the R groups of these molecules.